Hello. My name is Stephen Hawking, physicist, cosmologist, and something of a dreamer. Although I cannot move, and I have to speak through a computer, in my mind,
I am free. Free to explore the most profound mysteries of the cosmos, such as, why is the universe the way it is? Why does it follow rules and laws? Why is there order instead of chaos? Finding out leads us to the very deepest of secrets. To the one principle that's at the heart of everything in the cosmos.
check it out.
The recent excitement over the Higgs boson is just the latest step in a remarkable scientific voyage, one that has taken us into orbit and beyond. I've devoted my life to this quest because I believe it will lead us to the secrets of the universe itself.
This is the search for what I call the grand design. The key to the cosmos. The good news is, I think we found it. Almost. Getting here has
been quite a journey. It began one night 350 years ago in the small English town of Cambridge. The year was 1665. Death stalked the land as England fell under the plague's dark spell. A student called Isaac Newton fled town to escape the threat. We're fortunate he got away, because Newton was a radical thinker who dared to see the universe in a completely new way. Newton took the first steps in the search for the grand design by looking for the mysterious laws that govern nature. He asked, why do things move? Why do they stop? And most famously, why do they fall to Earth? You may not think answering such simple questions would change the world, but it did. Because Newton realized there was a force at work deep within the fabric of the universe that makes all objects attract one another, the force of gravity. Gravity works not just on Earth, but throughout the cosmos, and its strength depends on just a couple of fundamental things: the mass of the objects and their distance apart. To find his answers, Newton invented a completely new mathematical language called the calculus. You don't need to know how it works, but it wasn't bad for a 23-year-old. Scientists all over the world still use it every day. Newton's work made it possible to predict everything from the orbits of planets around the stars and the precise timing of eclipses to the trajectories of raindrops. Today, we theoretical physicists are still doing the same sorts of things as Newton. Only thankfully we don't have to worry about the plague. Although our work may seem complex, it's really quite simple. We're trying to unravel the hidden mechanism that underlies everything. We can only do this
because we stand on the shoulders of giants. Scientists who, piece by piece, discovered what makes the universe tick.
In the mid-19th century, another of my scientific heroes would make the next giant leap towards unraveling the key to the cosmos. Enter James Clerk Maxwell, a Victorian scientist who was fascinated by light. In 1861, his deep-found fascination with light led to him inventing color photography. He was so far ahead of his time, it would be another 30 years before the next full color photograph was taken. But that was just the beginning of what this remarkable man achieved. It was when he turned his attention to a different realm of physics that everything changed. This was the strange, almost magical connection between magnetism and electricity. There's nothing complicated about it. Move a magnet near a wire, and you will cause electricity to flow through the wire. Put electricity through a wire, and it will act like a magnet and deflect a compass. So what connected them? Maxwell's big idea was that magnetism and electricity are actually two facets of the same thing. A wave of energy that was part electrical, part magnetic. He called them electromagnetic waves. But then came a surprise. The mathematics told him these electromagnetic waves traveled at an extraordinary speed, 186,000 miles per second. The exact same speed that had already been determined to be the speed of light. This led to a stunning conclusion. Light is an electromagnetic wave too. Maxwell connected electricity, magnetism, and light in a series of 4 equations that I consider to be one of the greatest discoveries in the history of science. The equations, called Maxwell's laws, govern everything from the auroras that dance over the North and South Poles to the modern electrical and communications technology that powers the planet. Virtually every machine in the modern world, from a computer to a power station to a washing machine, works to the rules Maxwell revealed. Electromagnetism quite literally lights up our planet. A fitting testament to a great mind.
But light is much more interesting than even Maxwell himself realized. Although he didn't know it, he had actually uncovered one of the fundamental clues to the grand design. That clue is the speed of light itself.
By the late 19th century, it looked like some of the great mysteries of the universe would be all wrapped up, thanks to the groundbreaking discoveries of Newton and Maxwell. But then 2 American physicists stumbled into a completely unexpected discovery. Albert Michelson and Edward Morley were investigating the implications of Maxwell's revelation that light is a form of wave traveling at 186,000 miles per second. They figured that just as water waves are waves of energy traveling in water, and sound waves are waves of energy traveling through air, so light waves must also travel through something. They called this something the luminiferous ether. Michelson and Morley proposed that space, including the space between the sun and the Earth, was filled with this mysterious ether. They believed that sunlight must travel through the ether to reach Earth. Since the Earth also moved around the Sun, then it must be traveling through this ether too. If so, this movement would cause what they called an ether wind to blow over the surface of our planet. Michelson and Morley believed this ether wind should be detectable here on Earth, and designed an experiment to measure its effects. They ran their experiment in a cramped basement. But to understand the principle behind it, I thought we'd get them out of the lab and stage it out here on the beach. Since the Earth is constantly orbiting the Sun, then the ether wind would be ever present and would affect the speed of light here on Earth. If a beam of light was traveling with the ether wind behind it, the light should move faster. But if light was traveling in the exact opposite direction, and so was fighting the oncoming ether wind, the speed of light should slow down. And the difference between those two speeds should be measurable. But they couldn't detect any difference. Whichever way the light waves were pointing, they couldn't find any slowing down or speeding up. This result was deeply disturbing. The luminiferous ether could not exist. What's more, it meant the speed of light must be constant in all directions. Modern experiments have repeatedly confirmed this discovery. The speed of light remains fixed, regardless of the direction in which it is traveling. Michelson and Morley were deeply embarrassed about having to report they'd been wrong. The ether simply wasn't there. But the experiment wasn't a total disaster. It's one of the most important mistakes in the history of science.
Light is a wave that travels through nothing. What a strange idea. And the discovery that its speed cannot be varied is also very odd. Luckily, we physicists like strange things, because they often lead us to breakthroughs. It would take another of my heroes, Albert Einstein, to discover the deep truth about the nature of light. To explain how he did it, let me take you back to my
childhood. My old toy train is a perfect way of illustrating Einstein's profound questioning of what the fixed speed of light meant for the universe. Einstein started with a simple question. How fast is something like this little train moving? Well, this is the 1950s and toy trains weren't all that good. So let's say it's traveling at about 1 mile per hour. But change where you look at it from, and you get a different answer. The Earth spins on its axis at around 1,000 miles per hour. So seen from up here, my train is actually traveling much faster. But of course, the Earth as a whole is orbiting the Sun at 67,000 miles per hour. And even the Sun isn't stationary. It is orbiting the center of the Milky Way. And the Milky Way is moving through space too. So how fast is the train really moving? Well, it all depends on where you see it from. It could be 1 mile per hour, 1,000 miles per hour, 67,000 miles per hour, or many times faster. So what's the problem? Anyone can understand that speed is relative to your perspective. But when you remember that unlike the speed of the toy train, the speed of light is fixed, no matter what your perspective, then that common sense view of things starts to break down. To explain why, Einstein imagined a train too, only his was full-size. He devised a thought experiment, asking how something as simple as the lighting of a cigarette lighter would look to people with different points of view. He imagined a man playing with his lighter in the center of a railway car, being watched by two people at either end, both at exactly the same distance from the lighter. Einstein said the interesting question is not what do these two people see, but when do they see it? Because they're in the same car, all moving together at the same speed, the two observers see the light at exactly the same time. But what about someone outside? What does she see? From her perspective, with the train moving forward, the beam of light needs to travel a little bit further before it reaches the man at the front. On the other hand, the light moving towards the man at the back has a slightly shorter distance to go, since he is moving towards it. So she sees the light reach the man at the back before it hits the chap at the front. What that means is that an event on a moving train takes place simultaneously if you're on the train, but at different times when you're standing on the platform. Stop a moment and think about the implication of that. It means that we can't say if the events really happen at the same time or not. Reality itself depends on where you are. Scale this up to the universe as a whole, and it gets even weirder. If reality depends on where you are, then how can you know what's really going on in the universe?
What's more, what chance do we stand of finding the key to how the universe works if we can't even tell if two events are simultaneous or not? Don't worry, because Einstein thankfully came up with the answer in his famous theory of special relativity.
Einstein proposed that reality is flexible because time itself is flexible. It might sound strange, but this flexibility is just the start of a whole new concept in physics. Einstein went on to suggest that just like magnetism, electricity, and light, both time and space are inextricably linked in what he called space-time. This space-time is flexible as well. It can be bent and warped by the sheer mass of heavy things like stars and planets and galaxies. But what's really amazing is these distortions also explain that mysterious force discovered by Newton so many years ago. Gravity is the warping of space-time. Now, curving space and time may sound tricky to wrap your head around, but it's not. Imagine a boat locked on a straight course across the flat surface of a lake that stretches away forever. The flat lake is like undistorted space-time. Now imagine a giant hole appears beneath the lake and water begins to drain away. The lake has become distorted, just as space-time is by a planet. The effect would be to drag the boat towards the hole so that it begins to curve around it, even though the boat is still being driven in a straight line. And it's exactly that same effect a massive star or planet has on space-time. It causes space-time to distort around it, pulling things towards it. That's why things fall to Earth. Gravity.
Einstein had looked deep into the fabric of the universe and seen its inner workings. 10 years after he explained the fixed speed of light, he discovered that the distortion of space and time produces gravity, a fundamental force of nature. His work brought us much closer to discovering the secret key to the cosmos. But not even Einstein was prepared for what happened next.
Although Einstein had begun to reveal the universe's hidden clockwork, he still couldn't quite yet see how it operated. His theories drew on the nature of light as a super-fast electromagnetic wave racing through the emptiness of space. But they revealed nothing about what these waves really are. That challenge was taken up in 1919 by a German theorist named Theodor Kaluza, a mathematician with a passion for purity and elegance, the next great scientist in my pantheon of heroes. Kaluza was a man who took all forms of theory very seriously indeed. It's said that he taught himself to swim solely by reading a book on the subject. When it came to putting theory into practice, Kaluza was fearless. Luckily for Kaluza, the theory of swimming was well understood. But in 1919, that couldn't be said for a theory that explained the universe, a theory of everything. Inspired by Einstein's success in explaining gravity, Kaluza wondered if the same idea might be applied to electromagnetism and light. Were light waves ever more complex distortions of space-time, like ripples in the very fabric of the universe? It was a bold notion, and the answer was yes. Despite that flash of genius, Kaluza's timing was unfortunate. His ideas were swept aside by a new branch of physics that threw everything into question: quantum mechanics. This had happened when physics had turned its attention to studying some of the very smallest things in the universe. Inside the atom, the universe was revealed to be a strange, chaotic place where the familiar rules of physics just didn't seem to hold sway. Just how odd this quantum world was would be revealed in a deceptively simple experiment using tiny subatomic particles called electrons. A stream of electrons was fired through two tiny slits towards a detector. Common sense tells us the electrons should hit the detector in these two highlighted areas right behind the slits. But that's not what happened. Instead, the detector picked up a pattern of not just two lines, but many. This is simply not what anyone expected electrons or any small lumps of matter to do. The tiny electrons appeared to be defying the laws of physics. To get your head around just how weird this really is, let me scale up the electrons to something a bit more familiar, like a soccer ball. This striker is about to take a free kick. Obviously, he'll do his best to hit the ball past the defensive wall and the goalie and into the net. And they will do their best to stop that from happening. So far, it all makes sense. But apply the rules of the subatomic or quantum world and things work differently. And that's why physicists started to get very worried. Instead of taking a single, definable path, the ball, like the electrons, will take any and every route. Leaving the goalkeeper without a chance. Once in the goal, the ball reverts back to one reality. But in the moments before that, it is everywhere and anywhere. I told you it was weird. It's hard to overstate just how disturbing this view of reality is. If everything is actually chaotic at the subatomic level, then could the project started by Newton, continued by Maxwell, and refined by Einstein and Kaluza have boiled down to this? Something as random as a game of roulette. Perhaps the secrets of the universe are ungraspable and beyond the power of the human mind. The seeming contradictions between the chaotic workings of the subatomic world and the order of the rest of the world was a real problem for us physicists. But not for long. In the 50s, along came a man with an instinctive grasp of randomness and probability. Meet Richard Feynman, party animal, inveterate gambler, and something of a genius. Feynman brought the mathematics of his favorite vice to the uncertainty of the quantum world. He argued that just as a roulette ball obeys the laws of chance, so should an electron. As any roulette player knows, even though you can't predict for certain which number the ball will land on, you can work out the odds. 1 in 37, as it happens. Using probability, Feynman was able to deduce the peculiar rules that governed how a particular quantum event might unfold. With that, the quantum world was tamed and science itself brought back from the brink. Richard Feynman
did physicists a great favor. It's not just that some of his much-needed glamour rubbed off on us. His discovery that the quantum world could be predicted meant science could resume the search for the grand design. Physics now turned to finding connections between what happens at the very smallest scale to the universe at the very largest.
It did so by returning to the long-neglected work of that eccentric German physicist and self-taught swimmer, Theodor Kaluza. Physicists began looking at how his theories might apply to some of the tiniest things in nature. The world inside the atom, where electrons spin around a central nucleus composed of other particles, called neutrons and protons. Inside them are even smaller entities known as quarks. Quarks are themselves made from something we physicists call strings, which are ever more intricate distortions of space and time. You can think of them as being a bit like vibrating violin strings. Just as a violin string can vibrate to produce different musical notes, each subatomic string also vibrates, producing a different kind of fundamental particle. And it's these tiniest particles that give shape to the universe around us. Building on the ideas of Kaluza and Einstein, string theory suggests that the vibrations of the strings produce tiny distortions in space-time at a microscopic scale. And they do so in a mind-boggling 10 dimensions. If the string vibrates in one way, it produces a certain kind of fundamental particle, say a quark. And if it vibrates in another way, it creates a neutrino, which is another kind of particle. But here's the clever bit. String theory has the potential to explain why these particles interact with each other in the precise way they do, just like the harmony in a piece of music. And this is where the laws of physics come from. The laws that control everything, from the behavior of the newly discovered Higgs boson to a black hole, or the life and death of the stars. Take something as simple as a roll of paper falling to the floor, or the flickering of a magnetic compass needle, the simplest but most fundamental of actions, all governed by the rules of string theory. Of course, there is still work to do, as there are currently several different versions of this remarkable idea. Some versions of the theory only work at the very smallest of scales. Others only at very high temperatures, such as inside the core of an exploding star. Together we call this collection of theories M-theory. Nobody seems to know what the M stands for. It could be master, miracle, or mystery. Perhaps all three.
Either way, there's still lots of work to do. Physics has come a long way since Newton and Maxwell. And I must say I'm very glad to have lived through what I think will prove to be an historic turning point. At the Perimeter Institute for Theoretical Physics near Toronto, my colleagues and I have been thinking about what string theory could mean about our place in the universe.
One extraordinary prediction string theory is making is that there should be hundreds of billions of other universes. Perhaps more universes than there are stars in the known cosmos. To get your head round this, let's return to that idea that the strings of string theory are like notes played by a string quartet. Each vibration of the strings gives rise to the fundamental particles and to the forces of nature, which between them make up everything in the universe. But of course, the quartet could just as well be playing a different tune with different vibrating notes. And mathematically, that different tune would produce different particles and different forces of nature, meaning a different universe. Change again, and that's another universe. So just as there are an endless number of possible tunes, so our universe must be just one of billions of universes. We can't see them because they are beyond the limits of our own universe, each with their own history and properties. Some are unstable and collapse back to where they came from. Some will produce no stars or planets and so be dark and cold. Others will expand and go on to produce stars and galaxies like ours.
As we ponder this, we should not be surprised to find ourselves in a universe that is perfect for us. Our very presence means our universe must be just right. So the search for the key to the universe has had one unexpected result. We have found the key to every other universe too. It seems that M theory is the system of laws that governs everything. The grand design.